Picture, if you will, the very top of the world, seen from far above, where a great pale shape rests upon the dark sea like a slow, breathing lid of ice. Before we go any further, if you want a brand new Earth topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. From that high vantage, the Arctic Ocean does not look like an ocean at all. It looks like a smooth white country, scattered with cracks and seams, drifting in silence beneath a long, slanting sun. Hold that image in your mind for a moment. A floating skin of frozen seawater, thinner than a sidewalk in some places, thicker than a house in others, covering a sea the size of a small continent. It is not solid land. It is not soft water. It is something in between, something that drifts and turns, something that grows and shrinks with the breath of the seasons. And it sits there, year after year, at the quiet hinge of our planet. If you flew above it on a calm winter day, you would see a pale plain stretching to every horizon. The light would be low and golden, or perhaps dim and blue, depending on the hour and the month. Long shadows would fall from small ridges of broken ice. Thin black lines would cut across the white, where the ice has split and opened to the dark water below. Those black lines are called leads, and they appear and close again like slow seams in a vast quilt. The Arctic sea ice is enormous, and yet it is also delicate. In the depth of winter, it spreads across more than 14 million square kilometers. By late summer, much of it has melted away, leaving only a smaller core near the pole. This breathing rhythm, wide in winter, narrow in summer, has gone on for a very long time. Just how long and how stable that rhythm truly is remains one of the open questions of our age. That is the quiet mystery we will sit with tonight. The Arctic sea ice is changing. Satellites have watched it from above for only a few decades, which, in the life of an ocean, is hardly the blink of an eye. We can see that the summer ice has been shrinking. We can see that the old, thick ice is becoming rarer. But what comes next, and why exactly it is happening at the pace it is, and how the ice has behaved across the deeper centuries before our instruments, these questions are still being argued in quiet rooms by patient scientists. Some researchers think the Arctic could see ice-free summers within a few decades. Others think the ice may hold on longer than the simplest models suggest, protected by currents and winds we do not yet fully understand. Both groups are looking at the same white lid from above and asking the same question. The answer is not yet in. Now imagine drifting closer. From 30,000 feet, the surface seems smooth. From 3,000 feet, you begin to see the texture, the long pressure ridges where two floes have pushed against each other, the round pans of younger ice, the soft gray of fresh freezing water at the edges of the leads. From 300 feet, you would see how the snow lies on top in gentle dunes, sculpted by the polar wind into shapes that look almost like waves caught and held still. Closer still, the ice is alive in ways most people never picture. There are tiny channels inside it, threads of salty water that wind through the crystals. There are algae in those channels, painting the underside of the ice with faint streaks of brown and green. There are seals carving breathing holes from below. There are whales passing through the dark water beneath, singing their long, low songs. And above it all, the wind moves in a great slow circle, nudging the whole floating world in a turn that takes years to complete. This is what we will wander through tonight, The story of how this white lid forms, how it breaks, how it lives, how it speaks. The story of what scientists have learned and what they still cannot say for certain. The Arctic Ocean keeps many of its secrets in the cold. Some of them may be revealed in the coming years. Others may stay hidden far longer than we will be here to ask. For now, let your mind rest gently upon that high view, a pale lid drifting slowly, breathing with the seasons at the quiet top of the world. Settle in. The questions are kind ones. You can drift with them as long as you like. Salt water does not freeze the way fresh water freezes. That single fact is the door into almost everything strange about Arctic sea ice. If you pour a glass of tap water and set it outside in winter, it will turn to ice at a temperature of 0 degrees Celsius, which is 32 degrees Fahrenheit. The ocean does not follow that simple rule. The Arctic Ocean is salty, and salt gets in the way. The salt in seawater is mostly the same kind you sprinkle on food. It dissolves into tiny pieces and floats between the water molecules. Those tiny pieces make it harder for the water to lock together into a solid. So the ocean has to get colder before it can freeze. The usual freezing point of Arctic seawater is about -1.8 degrees Celsius, or just under 29 degrees Fahrenheit. Not much colder than fresh water, but enough to matter. When the ocean finally does freeze, something quiet and beautiful happens. The water molecules grab onto each other and start to form crystals. The salt, though, gets left out. It does not fit inside the crystal pattern. So as the ice forms, it pushes most of the salt back into the water below. The ice that floats on the Arctic Ocean is, slowly, becoming fresher than the sea it grew out of. This is why a piece of old Arctic ice, melted in a pot, tastes almost like drinking water. The salt has had years to drain away. New ice still holds little pockets of salty liquid, trapped inside its body like tiny veins. Those pockets are called brine channels. They are one of the smallest and most surprising worlds on Earth, and we will return to them later. The Arctic Ocean itself is the smallest of the 5 oceans. It covers about 14 million square kilometers, which is roughly the size of Russia, or about 1.5 times the size of the United States. It is shaped a little like a rough circle, ringed by land. Greenland, Canada, Alaska, Russia, and Northern Europe all lean their cold shoulders against it. In winter, ice grows from those shores and spreads outward until most of the ocean wears a white lid. That lid is thinner than people often imagine. First-year ice, the kind that forms in a single winter, is usually only 1 to 2 meters thick. That is about the height of a tall person standing up. Older ice, the kind that has survived several summers, can reach 3 or 4 meters. In places where slabs slam together and pile up, the ice can stack much higher, but the smooth, flat sheets across the open Arctic are surprisingly thin compared to the ocean below them. Below that thin skin, the water is deep. The Arctic Ocean averages around 1,200 meters in depth, and in its central basin it drops to more than 4,000 meters. That is deeper than most of the world's tallest mountains are tall, so the floating ice is a delicate ceiling over a vast, cold, dark room. The ice itself comes and goes with the seasons in a slow, patient breath. In March, near the end of the long polar winter, the ice reaches its largest size. It can cover around 15 million square kilometers, spilling out into the seas around it. By September, after the long polar summer, much of that ice has melted. The lid shrinks down to something closer to 4 or 5 million square kilometers in recent decades. Then the cold returns, and the freezing begins again. How long this rhythm has been going, in something like its current form, is itself an open question. The best evidence suggests that a permanent Arctic ice cap has existed for at least the last few million years. Some studies push that back further, to perhaps 13 or 15 million years. Other researchers wonder if the ice has been more on and off than we think, melting and reforming through long warm spells we are only beginning to understand. The record is patchy. The ocean does not keep neat diaries. What we can say simply is this: Arctic sea ice is a thin, salty, breathing skin of frozen ocean. It floats on water that is colder than fresh water would tolerate. It grows from the edges in, shrinks from the edges out, and carries inside it tiny rivers of brine that no one sees. It is not a continent of ice. It is not a glacier. It is the sea itself, learning, every winter, how to hold still. And the question of how long it will keep learning that trick is one we will sit with, gently, as the night goes on. To find the beginning of Arctic sea ice, we have to walk backward through time, not just a few years or a few centuries, but through long stretches of Earth's slow breathing. The white lid at the top of the world was not always there. For most of our planet's long story, the poles were warm. Crocodile relatives once swam in waters near the Arctic shore. Forests of strange, broad-leafed trees grew where today there is only ice and stone. Something changed. Slowly, gently, across many millions of years, the Earth grew cooler. The exact reasons are still debated by scientists. One leading idea points to shifting continents. As the great plates of the Earth's crust drifted into new positions, they rearranged the oceans. Warm water that once flowed freely toward the pole found its path blocked. The Arctic Ocean became a more enclosed sea, ringed by land, harder for warm currents to reach. Another idea looks to the air. Carbon dioxide, a gas that traps heat, slowly thinned out in the atmosphere over tens of millions of years. As the blanket grew lighter, the planet lost more warmth to space. The poles, already dim and slanting away from the sun, felt the cooling first. Most likely, both stories are true at once. The shifting land and the thinning air worked together, like two slow hands lowering the temperature of a room. Somewhere around 3 million years ago, give or take, the Arctic Ocean grew cold enough that a thin skin of ice could survive the summer. Before that, ice may have formed in winter and melted away by autumn. After that, some of it began to last. The white lid was born, not in a single year, but across countless slow seasons. To understand how this ice keeps itself alive, picture the polar night. For months at a time, the sun does not rise above the horizon near the pole. The sky moves through deep blues and violets, and then into a black so complete that the stars feel close enough to touch. The temperature falls. The wind moves across the dark water, pulling heat away from the surface. In this long, quiet darkness, sea ice has its true season of birth. The first crystals form where the cold air meets the cold sea. Tiny needles of ice, almost too small to see, drift in the upper layer of the water. Sailors and scientists call this stage phrasal. The water takes on a soft, oily look, as if a layer of gray silk has been laid across it. Slowly, the needles knit together. They form a slush, then a thin film, then a flexible sheet that bends with the swell. In the long polar night, this process can go on for weeks without interruption. There is no sun to warm the surface back. The cold simply deepens. The ice grows thicker from below as more water freezes onto its underside. A young sheet might add a few millimeters each day, then a centimeter, then more. Across a single winter, in the right conditions, the ice can reach 1 or 2 meters in thickness. What makes the Arctic special, though, is that some of this ice survives the brief summer. When the sun finally returns and climbs a little higher each day, the edges of the pack ice melt and break apart. But near the pole, the cold lingers. Floes that have lasted 1 summer become 2-year ice. Floes that last several years become old, thick, multi-year ice, sometimes 4 or 5 meters from top to bottom. That older ice is part of what makes the Arctic cap a true, lasting feature of the Earth, rather than a passing winter coat. It carries the memory of many polar nights. Each layer beneath its surface formed in a different year, in a different storm, under a different sky. How long this slow inheritance can continue is one of the open questions that runs through this whole story. The conditions that built the ice cap, cool air, blocked currents, long dark winters, are not fixed forever. They are still shifting, even now. Some researchers wonder whether the multi-year ice is the most fragile part of the system, the part most likely to thin and vanish first. Others suspect the winter ice itself may prove more stubborn than we expect. For tonight, it is enough to picture the beginning, a cooling planet, a quieter ocean. The first thin needles of phrasal knitting themselves together in the long dark, somewhere just below the pole. A white lid forming slowly, patiently, across more years than a human mind can hold. The polar night doing its quiet work. Imagine standing on the deck of a small ship far north on a still autumn evening. The sun is gone for most of the day now. The sea around you is dark and quiet, and then you notice something. The water has changed. It no longer shines like a mirror. It looks dull, almost oily, as if someone has spilled a thin film of soft wax across the surface. This is the first stage of sea ice. It has a name that fits its look. The polar scientists call it grease ice. Grease ice is made of tiny needles and plates of frozen water, each one only a few millimeters across. They float just at the surface, packed loosely together. When the wind blows, they slide and slosh in a slow, gentle motion. The sea looks like cold soup. If you dipped your hand in, you would feel a slush of fine crystals between your fingers. These small crystals carry no salt inside them. Pure water freezes first. The salt is pushed out, left behind in the seawater nearby. That salt is worth pausing on. The salt in the Arctic Ocean is mostly sodium and chloride, with smaller amounts of magnesium, calcium, potassium, and sulfate. These minerals have a long history, many of them washed off the land over billions of years, carried by rivers from rock to sea. The rock itself was built from elements forged inside long-dead stars. Iron, calcium, magnesium, the heavier atoms in the crust beneath your feet, All of them were cooked inside stars that lived and died before our sun was born. The Arctic Ocean is, in a way, a slow soup of starlight, stirred for ages by the wind and the moon. The water itself has its own deep story. Scientists still debate where Earth's water first came from. One idea is that much of it was already locked inside the dust and rock that built the young planet, and slowly seeped out through volcanoes. Another idea is that a great deal arrived later, carried by icy comets and water-rich asteroids that struck the early Earth. The truth may be a mix of both. The question is not fully settled. So when grease ice forms on the dark Arctic Sea, the water in those small crystals may, in part, have ridden here on ancient comets from the cold edges of the solar system. As the night deepens and the air grows colder, the grease ice thickens. The tiny crystals begin to bond. The surface stiffens into a thin, flexible skin called Nilas. Nilas is smooth and dark, sometimes almost black where it is thinnest. As it grows, it turns gray, then a paler gray, then white. You could push a finger through young Nilas with little effort, but it bends like rubber. When small waves roll under it, the whole sheet flexes in long, slow ripples, like a soft cloth being shaken. If the sea is rough while the ice is forming, something different happens. The young ice breaks apart again and again. The pieces bump and grind against each other in the swell. Each collision rounds their edges and pushes a small rim of slush up along the sides. What you end up with looks almost playful. Round, flat discs of ice, often less than a meter across, each one with a raised pale lip around the edge. They float together in great fields, gently knocking, slowly turning. The scientists call these pancake ice. From above they look like a giant tray of soft white plates laid out on the dark water. Inside these pancakes, the chemistry is busy. As the ice grows, it traps small pockets of brine, salty water too concentrated to freeze. It also captures tiny bubbles of air, mostly nitrogen and oxygen, the same gases you are breathing now. Some of those bubbles will stay locked in the ice for years, carrying a small sample of this season's atmosphere. In a sense, every flow is a slow, drifting archive. The pancakes drift together. Their edges meet and freeze. Slowly, over hours and days, the field welds itself into a continuous sheet of young ice. The pale rims still show, like faint scars in the new surface, a memory of how it began. From Greece to Nilas to Pancakes to a single quiet plain of ice, the sea has changed its skin. How exactly each of these stages connects, how much of the final ice carries the chemistry of each step, is still being studied. Researchers wonder how the trapped salt, the trapped gases, and the trapped life inside young ice shape what comes next. The recipe is partly known. The rest is still being read slowly, by patient hands in the cold. Out on the frozen ocean, not all ice is the same age. Some sheets formed only a few weeks ago, thin and dark and bending with the swell. Other slabs have drifted across the polar sea for years, growing thicker each winter, melting a little each summer, then thickening again. The story of Arctic sea ice is really the story of two kinds of ice living side by side. One is young and restless. The other is old and quiet and stubborn. The young ice is called first-year ice. It forms in the autumn when the sun slips low and the surface waters give up their heat to the dark sky. By spring, it can grow to about 2 meters thick. Then summer comes and most of it melts away. First-year ice is salty because it freezes quickly and traps pockets of brine inside its crystal cage. It tends to be flatter, smoother, and a little more brittle. Step out onto it, and you might see a faint gray cast running through the white. The old ice is different. Sea ice that survives at least one summer melt becomes what scientists call multi-year ice. Each year it loses a little salt as brine slowly drips downward through tiny channels. Each year it gains a little thickness from new freezing below. After several seasons, the salt is almost gone, and the ice becomes harder, denser, and a soft blue-green where it catches the light. Old floes can grow 4 meters thick or more. They feel almost like freshwater ice now, glassy and strong, the kind that rings when you tap it. These two kinds of ice respond to invisible forces in different ways. Wind pushes on the surface, currents tug from below. The slow spin of the Earth bends the ice paths sideways through something called the Coriolis effect, which simply means moving things on a turning planet curve gently to the right in the north. Tides rise and fall beneath the floes, breathing the whole frozen sheet up and down by tiny amounts every day. Gravity holds it all flat against the sea. Pressure builds where floes collide. Heat seeps up from the dark water below and escapes into the colder air above. Young ice yields easily to these forces. It bends, cracks, rafts up on itself, and rebuilds within hours. Old ice resists. When wind drives a thin floe against a thick one, the thin one usually loses, crumpling against the older slab and piling up along its edge. In this slow contest, the old ice acts almost like the bones of the Arctic, while the young ice grows around it like skin. For most of recorded history, multi-year ice made up the bulk of the central Arctic. Photographs and submarine sonar readings from the middle of the 20th century show a thick, ancient cap of ice covering the pole, ridged and rumpled, surviving summer after summer. In recent decades, that picture has changed. Surveys now suggest the ice has become younger on average, with far less of the very oldest, thickest ice than before. What this means for the future is one of the open questions running through this whole episode. Some researchers think the Arctic is shifting toward a seasonal system, dominated by first-year ice that grows each winter and melts each summer. Others wonder whether old ice can recover if cold years return. The honest answer is that no one is certain. Even the simple question of how old ice forms is more subtle than it first appears. One idea is that thickness alone makes the difference, and that any patch of ice surviving the summer simply continues to grow. Another idea places more weight on movement, suggesting that ice drifting into the calm, cold heart of the Arctic is more likely to age, while ice swept toward warmer outlets melts away before it can. Both ideas hold pieces of the truth. The full picture is still being assembled by scientists who measure ice from satellites, from icebreakers, from buoys frozen into the floes, and from autonomous robots gliding far beneath. There is something gentle about this rivalry between young and old. The forces at work are not violent, they are patient. A gust of wind here, a current there, a tide breathing under the white, salt slowly draining, crystals slowly knitting, floes slowly bumping. Over years, these small pressures sculpt a frozen world that no human eye can take in all at once. Somewhere out on the polar sea tonight, a slab of old, glassy ice is drifting in the dark, carrying with it a quiet history written in salt and silence and slow time. Imagine standing on the frozen surface of the Arctic Ocean. The ice looks flat from far away, like a great white floor stretching to the horizon. But come closer, and you find it is not flat at all. The ice is wrinkled, broken, and piled into long ridges that rise from the surface like the spine of some sleeping creature. These are called pressure ridges, and they hold one of the most surprising secrets about Arctic sea ice. What you see above the surface is only a small part of the whole. Pressure ridges form when two sheets of ice push against each other. The forces are slow but enormous. Wind drags one floe in one direction. A deep current pulls another floe the opposite way. When they meet, the ice cannot stretch or fold like cloth. It must break. The edges crack, splinter, and crumble. Slabs the size of cars pile on top of one another, building up into rough walls of broken ice. Above the surface, these walls can rise about 2 meters high on average. That is taller than a grown adult, but not by much. Some larger ridges reach 4 or 5 meters, the height of a small house. To a person walking across the ice, they look like long, jagged hills. They stretch for kilometers in some places, twisting across the frozen sea like the seams of a giant quilt. Here is the part that often surprises people. For every meter of ridge above the water, there can be 3 to 5 meters of ice below. This hidden underside is called a keel. It hangs down into the dark water like the bottom of a sunken wall. If a pressure ridge stands 2 meters tall above the surface, its keel may plunge 8 meters deep below. Larger ridges have keels that reach 20, 30, even 40 meters down. That is deeper than a 10-story building is tall. Picture it this way. If the visible ridge were the size of a loaf of bread sitting on a table, the keel beneath it would be the size of a refrigerator hanging below the table, out of sight. The Arctic Ocean is full of these hidden refrigerators, drifting slowly with the ice, scraping the cold water as they pass. The reason for this is simple physics. Ice floats, but only just. About 9/10 of any floating ice sits below the waterline. So when broken slabs pile up on top, an equal mass of ice must sink beneath to balance them. The sea hides most of what the ridge truly is. The scale of all this is hard to picture. A single pressure ridge can run for tens of kilometers. The total length of ridges across the Arctic, if you could lay them end to end, would wrap around the Earth many times over. Some studies suggest the ridges hold nearly half of all the ice volume in certain regions, even though they cover only a small fraction of the surface area. The flat ice between them, by comparison, is often only 1 or 2 meters thick. The ridges are where most of the mass lives. For submarines traveling beneath the Arctic ice, these keels are obstacles to navigate around. For seals, they are places to rest and hide. For the ice itself, they are sources of strength. A ridged floe is harder to break apart than a smooth one. The piled chunks freeze together over time, welded by cold and pressure into something stubborn and old. And yet, much about these ridges remains an open question. Researchers still wonder how exactly the keels shape the water below them. Do they stir the ocean enough to mix warm and cold layers? Do they slow the currents or steer them in ways we have not fully measured? Some studies suggest the deep keels create small swirls of turbulence as the ice drifts, pulling warmer water upward in tiny amounts. Others propose the effect is smaller than once thought. The picture is still being filled in. What we do know is that the Arctic ice is not a thin skin. It is a sculpted, three-dimensional structure, with valleys above and cliffs below. The roughness underneath is its own hidden world, dark and cold and rarely seen. Sonar maps from submarines have given us glimpses of this terrain, and the images look almost like an upside-down mountain range, with peaks pointing down into the deep. So when you picture the Arctic ice tonight, picture it whole. Picture the long ridges crossing the white surface like old scars. Picture the great keels hanging beneath them, silent in the dark water, holding more ice than the eye can ever see. Most of the frozen sea is hidden from above, drifting slowly, quietly, beneath the long polar night. Imagine yourself drifting above the Arctic Ocean on a calm winter morning, looking down at a vast white plain that stretches in every direction. From this height, the ice does not look smooth. It looks cracked. Long, dark lines wander across the surface like the veins of a great frozen leaf. These dark lines are called leads. They are openings in the sea ice where the floes have pulled apart, exposing the black water below. A lead can be as narrow as a footpath or as wide as a city street. Some stretch for hundreds of miles, curving and branching across the frozen sea. From above, they look like ink poured onto white paper. The water inside them is dark, almost glassy, and on a cold day, a thin mist rises from the surface. That mist is called sea smoke. It forms when the cold air meets the warmer water and pulls steam from it in soft, ghostly curls. Leads open and close with the movement of the ice. Wind, currents, and the slow turning of the great floes pull the ice apart in some places and crush it together in others. A lead may yawn open for a few days, then close again as the floes drift back. Sometimes a thin skin of new ice forms across the open water within hours, a delicate gray film that hardens slowly into a fresh sheet. In this way, the surface of the Arctic is always moving, always rewriting itself. If you came lower, close to the ice, you would see how the edges of a lead are sculpted. The floes meet the water in jagged shelves and broken slabs. Chunks of ice tilt at strange angles. Some pieces hang half-submerged, glowing pale blue beneath the surface. The colors are softer than you might expect. The ice is not pure white. It is gray, cream, faint blue, sometimes touched with the warm pink of a low winter sun. Then there are the larger openings, the ones that do not behave like leads at all. These are called Polynyas. A Polynya is a stretch of open water surrounded by ice, and unlike a lead, it can stay open for weeks or even months in the middle of winter. Some Polynyas are small, others cover thousands of square miles. They appear in roughly the same places year after year, as if the sea has memory. Scientists describe two main kinds. One forms when strong winds blow ice away from a coastline, leaving open water behind. These are called latent heat Polynyas, because new ice keeps trying to form and gets pushed away again. The other kind forms when warmer water rises from below and melts the ice from underneath. These are called sensible heat Polynyas. Why certain Polynyas return to the same spots, season after season, is still partly an open question. The exact mix of wind, current, and underwater terrain that creates each one is not fully understood. What is known is that Polynyas matter. They are gathering places. Seals breathe at their edges. Walruses haul out on the nearby ice. Whales surface in the open water, sending pale plumes of breath into the cold air. Seabirds wheel above them in great numbers. A Polynyaa in midwinter is one of the few places in the Arctic where life can find both air and food in the long dark. Some researchers wonder whether ancient peoples followed these Polynyas across the frozen sea, using them as moving oases. From above, a Polynyaa looks like a dark lake set into a white field. Its edges are ragged and ever-shifting. Steam rises from it in thick clouds when the air is very cold, so that from far away it can look almost like a slow fire burning on the ice. The light around it changes the longer you watch. The water reflects the sky in deep blues and silvers, and the surrounding floes catch the low sun in soft golds and lavenders. If you stood on a floe at the edge of a lead, you would hear sounds you might not expect. The ice creaks, water laps quietly against the shelf. Sometimes a far-off boom rolls across the surface as a distant floe cracks. The Arctic surface is not silent. It is a slow, breathing thing, opening and closing, gathering steam, drifting beneath a pale sky. How leads and Polynyas will behave in a warmer world is one of the open questions. Some studies suggest leads are growing more common as the ice thins. Others find the patterns harder to pin down. The surface of the Arctic keeps moving, keeps reshaping itself, and the full story of its dark seams and open windows is still being written. Beneath the white surface of the sea ice, something quiet and strange is happening. If you could shrink yourself small enough to slip inside the ice itself, you would find that it is not solid at all. It is more like a frozen sponge, threaded with tiny tunnels and pockets. And inside those pockets, a heavy, salty liquid is slowly making its way down. This liquid is called brine. When seawater freezes, the ice crystals form from pure water and push the salt away. The salt has nowhere to go, so it gathers into little droplets and channels trapped inside the growing ice. These pockets are very cold and very salty. Some of them are saltier than the saltiest sea on Earth. They stay liquid even at temperatures that would freeze normal ocean water solid. Over time, gravity tugs at these heavy pockets of brine. They begin to seep downward through the ice, drop by drop, following narrow channels carved through the frozen layers. The brine is colder and denser than the seawater below. When it finally drips out of the underside of the ice, it sinks like an invisible thread falling into the sea. In rare moments, this dripping brine creates one of the strangest sights on the planet. As the cold, salty stream sinks into slightly warmer ocean water, the water around it freezes instantly into a fragile tube of ice. The tube grows downward, following the falling brine, sometimes all the way to the seabed. Divers have called these formations brinicles. They look like pale, hollow icicles reaching down into the dark. Where a brinicle touches the sea floor, it can freeze small creatures that cannot move away in time. The ice spreads outward across the bottom in a slow, ghostly bloom. Brinicles are rare and hard to study. They form only in calm, shallow places where conditions are just right. Most of the brine that escapes the ice never makes a visible tube at all. It simply slips away into the dark, mixing into the deep currents below. This quiet dripping matters more than it seems. The brine is heavy enough to sink far down into the water column. As it sinks, it helps drive the slow stirring of the polar seas. Cold, salty water rolls downward. Lighter, fresher water rises to take its place. This is one of the small engines that helps move water across the whole world ocean. The exact size of that engine and how it might change as the ice changes is still being studied. Researchers have measured brine flow in many places, but the full picture of how much it shapes the global circulation remains an open question. Inside the ice itself, the brine channels are tiny worlds. They are filled with a dim, bluish light that filters down from above. Strange communities live in them. Single-celled algae cling to the channel walls. Tiny shrimp-like creatures crawl through the wider passages. Bacteria that can survive in extreme salt and cold drift in the liquid. Some of these microbes are unlike anything found in warmer waters. Scientists wonder if studying them might help us understand how life could survive in salty, icy places elsewhere, like the frozen oceans suspected on certain moons. For now, the question stays open, and the little channels keep their secrets. The structure of the ice from above down to its underside is not uniform. Near the top, the ice is colder and harder, and the brine pockets are small. Near the bottom, where the ice meets the sea, the ice is warmer and softer. The brine channels there are wider and more connected. This lower layer is sometimes called the skeletal layer. It is mushy and fragile, almost more slush than ice. It is also where most of the life lives, hanging from the underside of the floes like a soft garden. How fast brine drains, how the channels grow and close, how the skeletal layer behaves through a winter, all of these are still being worked out. Each ice flow is a little different. The story of one piece of ice is not quite the story of another. Researchers drill cores and lower instruments through holes cut in the surface, trying to piece together what is happening in the layer no one can easily see. So while the white surface above looks still and silent, the underside is alive with slow motion. Brine drips, channels shift, tiny creatures move through liquid that should not be liquid at all. Somewhere, perhaps right now, a brinacle is forming in the dark, growing downward one fragile inch at a time, and we are only beginning to understand what it means for the wider sea. Snow falls gently on the frozen sea. It drifts down in soft, slow flakes through the long polar twilight, and it settles on the ice like a quiet second skin. This snow layer is thin in some places and thick in others, shaped by the wind into low dunes and smooth fields. And though it looks like a simple white blanket, it changes almost everything about how the ice lives, breathes, and reflects the world above it. The cycle begins each autumn. As the sun dips lower and the air cools, the first snows arrive on the new young ice. At first, the flakes melt where they touch the slightly warmer surface. Then, as the cold deepens, the snow begins to stick. Layer by layer, week by week, it builds. By midwinter, the snow on Arctic sea ice may be a few inches deep, sometimes more, sometimes less, depending on the wind, the storms, and the shape of the ice below. This snow does something quietly powerful. It works like a thick wool blanket on a cold night. It traps the ice's small warmth and slows the loss of heat to the bitter air above. Without snow, the ice would grow thicker much faster, because the cold could reach down through it and freeze more seawater from below. With snow, the ice grows more slowly. The snow protects the ice in a strange way from the very cold that made it. Then comes the spring and the cycle turns again. The sun returns to the high Arctic after months of darkness. Its light is low and slanted, but it is constant. And here the snow does something else surprising. It reflects almost all of that sunlight back into the sky. Fresh snow can bounce back 9 of every 10 rays that touch it. Scientists call this quality albedo, which simply means how bright and reflective a surface is. The brighter the surface, the more sunlight it sends away and the cooler it stays. So through the spring, the snow keeps the ice cold even as the sun grows stronger. It is a kind of slow shield, but snow does not last forever. As temperatures creep upward, the snow begins to soften. Tiny puddles appear on the surface. These are called melt ponds. They are pale blue or deep turquoise, and they spread across the ice in shallow pools that shimmer in the long Arctic daylight. Melt ponds change the cycle dramatically. Where the snow once reflected most of the light, the dark water of the ponds drinks it in. The pond absorbs warmth. It grows. It melts more ice beneath it. And so a small change in the snow becomes a larger change in the ice. The bright shield gives way to a darker, thirstier surface, and the summer melt accelerates. Researchers have wondered for a long time about the precise timing of this shift. When exactly does the snow finish its protective work and begin to fail? How does the depth of the snow each winter shape the size and number of melt ponds the next summer? The answers are not fully known. One idea is that thicker winter snow leads to bigger ponds later, because there is more water to release. Another idea is that the shape of the ice beneath matters more than the snow above. The question stays open. The cycle is real, but the fine details still puzzle the people who study it. And there is something else hidden in the snow, the way snow bends light. When sunlight passes through snow and then through ice, it scatters and softens. The light that reaches the sea below is not the same light that fell on the surface. It is bluer, dimmer, gentler. This filtered light is what feeds the tiny algae that live within and beneath the ice, the first quiet link in the long Arctic food chain. The snow, in this sense, is not just a blanket. It is a kind of slow lens, shaping the light that brings life to the dark water. Each year the cycle repeats. Snow falls, snow protects, sun returns, snow reflects, ponds form, ice melts, open water spreads, and then as autumn closes in again, the seawater freezes anew and the first soft flakes drift down once more. It is a rhythm older than any record, a breathing in and breathing out at the top of the world. How long this rhythm will hold its familiar shape is one of the quiet questions of our time. The snows still come. The ponds still form, but the timing, the depth, the duration, these details may be shifting in ways we are only beginning to understand. For now, the cycle continues, soft and slow, beneath the long northern light. Below the ice, the world does not go still. It only grows quieter, dimmer, and a little more strange. The frozen ceiling looks empty from above, but its underside is a living surface, textured with ridges and pockets and pale brown stains where tiny plants cling. To the creatures down there, the ice is not a roof. It is a kind of inverted seafloor, hanging in the sky of their world. The smallest neighbors are the easiest to overlook. Ice algae grow on the rough lower edge of the floes, painting them in soft amber and olive smears. These tiny plants gather what little light slips through the snow and ice above. They form long, drifting strands that dangle down into the cold water, almost like fine hair. In spring, when the sun returns, these strands bloom in slow motion, feeding the smallest grazers in the sea. Among those grazers are copepods, pale specks no bigger than a grain of rice. They drift in vast clouds beneath the ice, sipping algae and storing fat in oily droplets inside their bodies. Those droplets matter more than they seem. The fat becomes fuel for almost everything larger. Arctic cod eat the copepods, seabirds eat the cod, seals eat the cod too, and bigger animals eat the seals. The whole tall tower of polar life rests on these small, bright lives beneath the floes. The Arctic cod is a quiet wonder of its own. It is slim and silver, hardly longer than a hand, and it tucks itself into the cracks and grooves on the underside of the ice. Some researchers think the ice gives it shelter from larger fish and from the hunting beaks of seabirds above. Others suspect the cod simply follows its food, the copepods, which gather where the algae grows thickest. The truth probably mixes both ideas, and parts of the cod's life still slip past us. No one has fully watched a winter in its world. Higher up the chain swim the ringed seals, the small spotted seals that carve breathing holes through the ice with the claws on their front flippers. They keep these holes open all winter, scraping away the new ice that tries to seal them shut. A single seal may tend several holes scattered across the floes, traveling between them under the dark water. In spring, mother seals dig snow caves above the holes and raise their pups in soft, hidden rooms made of snow. From below, the ice is their ceiling. From above, the snow is their roof. They live in the seam between two frozen worlds. Larger still are the bearded seals, heavier and slower, with long pale whiskers that sweep the muddy seafloor for clams and shrimp. Their deep, looping calls carry for many miles under the ice in spring. Walruses gather on the edges of the pack in places where it is shallow enough for them to dive and feed. They prefer thin, broken ice that can hold their weight while still letting them slip easily into the sea. How they choose one floe over another, and how they remember good feeding grounds across years, are questions that remain only partly answered. Then there are the great whales. Bowheads cruise slowly along the edges of the ice, their thick blubber and massive skulls letting them push up through floes a foot thick to breathe. Belugas, small and white and social, travel in loose pods through the leads, their chirps and whistles painting the water with sound. Narwhals follow deep cracks far into the pack, diving to the dark seafloor in search of squid and halibut. They spend more of their lives among heavy ice than almost any other whale. What the narwhal's long spiral tusk is truly for is still debated. Some think it senses changes in the water. Others think it is mainly used in gentle contests between males. The mystery has not been settled. Above the ice, the gulls and guillemots wheel and dive at the open leads, plucking cod from the surface. Below, an unseen world of jellies, amphipods, and tiny shrimp drifts in slow currents shaped by the ice itself. Each layer leans on the one beside it. The algae feeds the copepods. The copepods feed the cod. The cod feeds nearly everyone else. Pull out one thread, and no one yet knows exactly how the whole soft fabric would change. That uncertainty is part of why scientists watch this hidden community so closely. The frozen ceiling is not just frozen water. It is a shelter, a pasture, a nursery, and a hunting ground, all stacked together in the cold and the quiet. And much of what happens beneath it, in the long polar dark, still passes unseen. Of all the creatures that live with the Arctic ice, none has captured the imagination quite like the polar bear. The largest land carnivore on Earth, a male polar bear can stretch 10 feet from nose to tail and weigh more than 1,500 pounds. He walks across a surface that is not land at all, but a thin floating skin of frozen seawater over a deep, cold ocean. In a way, he is a creature who has learned to walk on water. Scientists who study these bears have long called them marine mammals, even though they do not live in the sea the way a seal does. They live on top of it. They hunt on it, they mate, travel, and rest on it. Some bears spend nearly their entire lives without setting foot on solid ground. The sea ice is their floor, their hunting field, and their highway. Their bodies have shaped themselves to this strange world in ways that still surprise researchers. A polar bear's skin is not white but black, the color of old soot. The fur above is not white either. Each hair is hollow and clear, and the white we see is only a trick of light scattering through those tiny tubes. One older idea suggested the hollow hairs might pipe sunlight down to the dark skin like fiber optic cables. That idea was tested and mostly set aside, but the real reason for the hollow hairs is still debated. Some researchers think they trap warm air. Others wonder if they help the bear float in icy water. The question is not fully closed. Polar bears can swim for astonishing distances. One female, fitted with a tracking collar, was followed across more than 400 miles of open Arctic sea in a single continuous swim. She paddled for 9 days without rest. When she finally hauled out, she had lost a fifth of her body weight. How she navigated, how she kept warm in water near the freezing point, how she did not drown from exhaustion, these are questions biologists still puzzle over. The bear simply did it and then walked on. Beneath the ice, the bears hunt seals with a patience that seems almost endless. A bear may stand motionless beside a small breathing hole for hours, sometimes for an entire day, waiting for a single moment when a seal rises for air. The sense of smell that guides them is among the keenest in the animal kingdom. Some studies suggest a polar bear can detect a seal through 3 feet of solid ice and snow from more than half a mile away. How exactly they pick the scent of one warm body out of the cold polar wind is not fully understood. The chemistry of that detection is still being mapped. The cubs are born in the deep heart of winter, inside snow dens hollowed into drifts on land or on thick shorefast ice. They emerge weighing less than 2 pounds, smaller than a loaf of bread, blind and nearly hairless. By the time they leave the den a few months later, they may weigh 30 pounds. The mother during this time does not eat, does not drink, and barely moves. She lives entirely off her stored fat while feeding her cubs the richest milk produced by any land mammal. How her body manages this long fast without harm is another quiet puzzle of polar biology. Polar bears are not the only extremists of this frozen world. The bowhead whale, which lives year-round in Arctic waters, may be the longest-lived mammal on Earth. Harpoon points from the 19th century have been found embedded in living bowheads, suggesting some individuals swimming today were already adults when sailing ships still hunted them. Estimates of their lifespan reach 200 years and possibly more. The exact ceiling is still unknown. The Arctic cod, a small silver fish that feeds many of these larger creatures, carries a kind of natural antifreeze in its blood. Special proteins lock onto tiny ice crystals before they can grow, keeping the fish liquid in water that would freeze any ordinary blood solid. Researchers are still working out exactly how these proteins evolved and how many other Arctic species use similar tricks. So the ice is not empty, and it is not silent, and it is not gentle. It is a stage for some of the most remarkable bodies and behaviors on the planet. A bear who walks on water. A whale who outlives empires. A fish whose blood will not freeze. And around them all, the slow white ceiling drifts and groans, hiding more questions than it answers, holding its quiet records under the long polar sky. Far below the wind and the snow and the wide white plain of the ice, there is another world. It lives in the cracks. It lives in the tiny channels of salty water that thread through every floe, and it is green. Sea ice is not the solid block it looks like from above. When the water freezes, it pushes out most of its salt, but not all. Tiny pockets of very salty water stay trapped inside the ice. These pockets connect like a network of small tunnels and rooms. Scientists call this the Brine Channel system. It is, in a way, a hidden city. Inside that city live the ice algae. They are some of the smallest plants on Earth. Most are single cells, far too small to see without a microscope. Under the lens, they look like tiny golden brown jewels. Some are shaped like long, thin needles. Some look like little stars. Some are shaped like ribbons, twisting slowly in the dark brine. Many belong to a group called diatoms, which build delicate glass shells around themselves out of silica. Those shells are patterned with holes and ridges so fine, and so even that early scientists thought they must have been made by tiny artists. The algae cling to the bottom of the sea ice, where the brine channels open into the cold sea below. From above, looking down through a hole drilled in the floe, you might see the underside of the ice glowing a soft brown-green, like an upside-down meadow. In some places, this layer grows so thick it hangs down in long strands, swaying with the slow current. Divers who have swum beneath the ice describe it as drifting through a forest turned on its head, a quiet forest, a still one. What the algae do is small and patient. They take in the dim light that filters down through the snow and the ice. They use it to grow. They are the first link in a long chain of life under the floes. Tiny shrimp-like creatures called amphipods graze on them. Small fish called Arctic cod feed on the amphipods. Seals feed on the cod. Bears feed on the seals. The whole bright shape of Arctic life rests, in the end, on a soft brown smear at the bottom of the ice. And here the mystery begins to gather. no one is entirely sure how much light the algae need. The bloom often starts in early spring, when the sun barely rises above the horizon and the ice above is still covered in deep snow. Almost no light should reach them, yet they begin to grow. Some researchers wonder if the algae have found ways to survive on light levels so faint we can barely measure them. Others wonder if they can sip on chemicals dissolved in the brine when light is too weak. The question stays open. There is also the question of where they come from each year. When the ice melts in summer, the algae fall into the sea. Some sink to the seafloor. Some are eaten. Some drift in the cold, dark water. When new ice forms in autumn, the algae appear again inside it, almost as if invited. How they find their way back into the freezing brine, and which cells become the seeds of next year's bloom, is something scientists are still working out. Under a microscope, the diversity is startling. A single thumbnail of ice can hold dozens of species, each with its own shape and its own quiet job. Some make a kind of natural antifreeze, a sugary substance that keeps their cells from bursting in the cold. Some join together in long chains that look like tiny strings of beads. Some glide, some simply wait. There are even smaller things in the brine: bacteria, viruses, microscopic animals that swim through the salty tunnels like creatures in a flooded cave system. A whole ecosystem, folded into a space no thicker than a sheet of glass. Most of it has never been named. Some of it has never been seen at all. When researchers pull up a core of sea ice and slice it open, they see bands, layers of clear ice, layers of cloudy ice, and near the bottom, a soft golden-brown stripe where the algae live. It is one of the prettiest things in polar science, they say, a small, glowing line in a frozen world. So while the bears walk above, and the whales sing below, and the wind moves across the great white plain, the cracks themselves are alive. Quietly, slowly, in ways we are still learning to see, and the listener, drifting now towards sleep, may picture that gentle green light hidden under all that ice, patient in the dark. For most of human history, the Arctic was a place known only along its edges. The people who lived in the far north knew the ice in deep-lived ways. They read its colors and listened to its sounds. But the wider world, the world of maps and ships and written records, took a long time to understand what the frozen ocean was actually doing. The slow learning of the Arctic's seasonal pulse is a story of patience, frostbitten instruments, and many quiet mistakes. The earliest seafarers from southern lands met the ice as a wall. Norse sailors, more than 1,000 years ago, wrote of a sea that turned to stone in winter and softened in summer. They had no instruments to measure it. They only knew that some years the ice came farther south and some years it pulled back. Whalers in the 1600s and 1700s began to keep simple logbooks. They wrote down where the ice edge sat each month. Without meaning to, they created the first long record of the Arctic's breathing in and out. By the 1800s, expeditions began to push deeper, often paying a heavy price. Wooden ships were squeezed and broken by the moving floes. Crews wintered over in tiny cabins, watching the dark months pass. Some of these voyages ended in tragedy, and we will speak of them softly later. But even the lost ships left behind notebooks and sketches. Some of those notebooks drifted home in the pockets of survivors, or were found years afterward in cairns of stone. From them, scientists slowly began to see a pattern. The ice grew each autumn, it shrank each spring, it moved. That last part, the movement, was the great surprise. For a long time, people imagined the polar sea as a fixed white cap. Then, in the 1890s, a Norwegian explorer named Fridtjof Nansen tried something strange. He built a wooden ship with a rounded hull, designed to be lifted up by the ice rather than crushed by it. He let his ship freeze into the floes on purpose. For 3 years it drifted with the ice, carried by currents no one had mapped. When it finally emerged on the other side of the polar basin, the world learned that the ice was not still at all. It flowed in slow, vast rivers across the top of the planet. Other instruments followed. Simple thermometers lowered through holes in the floe began to reveal the layered water below. Early sounding lines, weighted ropes dropped through cracks, hinted at the deep keels of pressure ridges hanging into the dark. Scientists at coastal stations learned to mark the day the ice first formed each autumn and the day it broke up each spring. These dates, kept year after year in small notebooks, became one of the most valuable records we have. The truly clear picture came only with eyes from above. In the 1970s, satellites began to watch the Arctic from orbit, sweeping across the pole again and again. For the first time, the whole white lid could be seen at once. The seasonal pulse, which earlier sailors had only glimpsed in fragments, became visible as a single slow rhythm. The ice swelled in March. It shrank to its smallest in September. Then it began to grow again, in a cycle as steady as breathing. Yet even with these new eyes, much remained uncertain. Satellites could see the surface, but not the thickness. Was a given patch of ice thin and young, or thick and many years old? That question stayed open for decades. Submarines passing beneath the floes during the Cold War gathered some of the earliest thickness measurements by bouncing sound up at the underside of the ice. Their records, kept secret at first, were later shared with researchers. Even now, the full history of how thick the ice once was and how that has changed depends on stitching together submarine logs, satellite scans, and the careful drill holes of field scientists camping on the floes. Each new instrument has answered some questions and opened others. We can now watch the ice move in near real time. We can measure its salt, its temperature, its age. And still, when scientists try to predict what next September will bring, the answers come with wide uncertainty. The Arctic does not always behave the way the models expect. Some years the ice retreats farther than anyone guessed. Other years it lingers. The pulse of the seasons is real, and we have measured it carefully. But the rhythm itself seems to be changing in ways we do not fully understand. The history of Arctic discovery is, in the end, a history of learning how much we still have left to learn. Most of us picture sea ice as something still, a frozen surface, locked in place, sleeping through the long polar night. But the ice at the top of the world is never still. It drifts, it travels. It crosses entire oceans on a slow, patient march that can take years to complete. A single piece of ice can be born off the coast of Siberia, in the shallow seas above the Russian shelf. It freezes in autumn, thickens through winter, and begins to drift. Pushed by wind and current, it moves north, then west, then slowly across the top of the planet. After 2, 3, sometimes 4 years, that same piece of ice may slip out through the gap between Greenland and Svalbard, melting at last in the warmer waters of the North Atlantic. Its whole life is a slow walk across the pole. Scientists call this great river of ice the transpolar drift. It is one of the most important currents on Earth, and yet it moves so quietly that for centuries no one knew it existed. The story of how we learned about it is a quiet one. In the late 1800s, a Norwegian explorer named Fridtjof Nansen noticed something strange. Wreckage from a ship that had been crushed by ice off the coast of Siberia had washed up, years later, on the shores of Greenland. The wood had traveled thousands of miles, but no human had carried it. The ice itself had been the boat. Nansen wondered if a ship could ride that same current. He built a vessel with a rounded hull, designed to be lifted up rather than crushed when the ice closed around it. He let the ice freeze his ship in place, and then he waited. For 3 long years, his ship drifted with the floes, pulled by an invisible hand across the polar sea. He never reached the pole itself, but he proved the current was real. What makes this drift so strange is how slow it is and how patient. The ice moves only a few kilometers each day. Sometimes it pauses, sometimes it shifts direction with the wind, but over years the pattern holds. A great slow conveyor, carrying ice from the Siberian side of the Arctic, across the top of the world and out into the Atlantic. The ice carries things with it, sediment picked up from shallow coastal waters when the ice first formed. Dust from distant deserts, blown north and trapped on the frozen surface. Sometimes even small stones, lifted by freezing mud and rafted across the ocean. When the ice finally melts off the coast of Greenland, it drops these tiny travelers onto the seafloor. Geologists studying old sediment cores can sometimes trace a single grain back to a riverbank in Siberia, thousands of kilometers away. There are other currents too. On the North American side of the Arctic, a great slow whirlpool turns clockwise, holding ice in place for years at a time. We will sit with that one in the next section. But the transpolar drift is the long-distance traveler, the walker. The current that crosses the pole, and here is something that even researchers find strange. The drift seems to be speeding up. Satellite measurements over the last few decades suggest that ice is moving across the Arctic faster than it used to. Some scientists think this is because the ice itself has grown thinner and lighter, easier for the wind to push. Others wonder if changes in the wind patterns themselves are doing the work. The two ideas overlap. They may both be true at once. The question of which matters more remains open. A faster drift means ice spends less time in the Arctic before melting. Old ice, thick ice, the kind that builds up over many winters, has less chance to survive. This may be one reason the ice cover has been changing so much in recent decades, but the full picture is still being assembled. The currents, the winds, the temperature of the water below, the snow on top, all of these things speak to each other in ways we are only beginning to understand. For tonight, it is enough to picture it. A single floe of ice born in the dark off a Siberian shore, drifting north under the stars, crossing the pole in silence, carrying its tiny cargo of dust and stone. Years pass, the world turns. And one quiet morning, the floe slips into warmer water and dissolves, releasing its long-held travelers onto the seafloor below. The ice never knew it was moving, but it crossed the top of the world all the same. North of Alaska and Canada, in the wide bowl of sea that sits above the continental shelves, a slow wheel turns in the water. It is called the Beaufort Gyre. It is a great, lazy spinning of the upper ocean, shaped like a soft circle hundreds of miles across. The ice that floats on its surface turns with it, drifting clockwise through the long polar year. The wheel turns so slowly that a single piece of ice may ride around it for many seasons before it ever finds the edge. The gyre is driven by wind. High in the sky above the Arctic, a region of high pressure often sits over the Beaufort Sea, and the winds that curl around it press down on the surface of the ocean and on the ice itself. Those winds shove the ice in a steady clockwise pattern. The ice, in turn, pushes on the water below. The water responds with its own slow turning, dragging deeper layers along with it. In this way, air and ice and ocean speak to one another in a quiet, circular conversation. The Beaufort Gyre does something remarkable. It stores fresh water. As ice melts at its edges, and as rivers from Siberia and North America push their cold flow into the polar basin, the gyre collects that fresh water and holds it in a dome. The center of the gyre actually rises slightly, lifted by the spinning, like tea slowly stirred in a wide cup. Beneath the surface, a vast pool of cool, fresh water sits cradled in the turning. Some studies suggest the gyre now holds more fresh water than it has in many decades. What happens to that fresh water when the wheel slows or reverses is one of the open questions of Arctic science. Every so often, the winds shift, the high pressure weakens, or the pattern flips. The gyre slows. When it slows enough, some of the fresh water it has been holding can spill outward, sliding south through the gaps between Greenland and the islands of the Canadian Arctic. From there, it can reach the North Atlantic. This matters because the North Atlantic is where some of the world's deep ocean currents are born. Cold, salty water sinks there, and that sinking helps drive a vast, slow circulation that carries heat around the planet. A sudden flood of fresh water into that region could, in theory, change the saltiness of the surface and slow the sinking. Some researchers wonder whether past releases from the Arctic have nudged the climate of Europe and the North Atlantic in centuries gone by. The evidence is incomplete. The connections are hard to measure directly. The question remains open. The gyre also touches the ice in another way. Old ice, the thick, multi-year kind, used to gather in the heart of the Beaufort wheel. The slow turning kept it there, year after year, letting it thicken and harden under endless winters. In recent decades, that storage seems to have changed. More of the old ice is breaking up, drifting out, or melting in summer waters that have grown warmer. The wheel still turns, but what it carries has shifted. There is a sister current, too, called the transpolar drift, which runs in a roughly straight line across the top of the world, from the Siberian side toward the gap between Greenland and Svalbard. The Beaufort Gyre and the transpolar drift work together like two gears. Ice can ride the gyre for years, then slip into the drift, and then be carried out of the Arctic entirely, melting at last in the warmer salt of the Greenland Sea. A single floe, born in a quiet bay one winter, may travel thousands of miles before it finally disappears. All of this connects to the sun in ways that are easy to forget. The winds that drive the gyre are themselves shaped by the uneven heating of the planet. The warm tropics, the cold poles, the spinning of the Earth, these are the deep engines behind the gentle clockwise turn at the top of the world. The sun, the air, the ice, the salt, the rivers, the deep ocean far below, all of them are joined in one slow piece of music. What no one can yet say with full confidence is how the music will change as the Arctic warms. The gyre may strengthen, it may weaken, it may release its stored fresh water in a long, slow trickle or in a sudden pulse. Some models lean one way, some another. For now, the wheel keeps turning beneath the stars and the long polar nights, holding its quiet secrets in a pool of cold, soft water no one has fully measured. Far from the open sea, deep in the heart of Greenland and the high islands of the Canadian Arctic, lie long cylinders of ice pulled gently from the land. These are ice cores. Scientists drill them from glaciers and ice sheets, lifting out slender columns that reach down through layer after layer of ancient snow. Each layer was once a snowfall on a quiet polar day, long before any human lived to see it. And each layer holds tiny bubbles of trapped air, sealed inside the ice like little time capsules. The deepest cores reach back hundreds of thousands of years. When researchers slice them open and study the bubbles, they are tasting the breath of old skies. They can measure how much carbon dioxide was in the air. They can measure how much methane drifted through ancient winds. They can even guess at the temperature of long-vanished winters by reading the chemistry of the ice itself. In this slow, patient way, the polar ice keeps a record of the world. The ice cores from land are not the same as sea ice. Sea ice is too young and too restless to hold a long memory. It forms, drifts, melts, and forms again, season after season. But the land ice nearby tells the story of what the Arctic climate has been doing for a very long time. And by reading that story, scientists try to understand what sea ice may have looked like in ages past. The record shows that the Arctic has changed many times. There were long, cold stretches when ice gripped the north far more tightly than it does today. Glaciers crawled south. Sea ice may have spread further and lingered longer. Then there were warmer pauses, called interglacials, when the planet softened and the ice pulled back. Some of those warm spells were gentler than now. Some may have been warmer still. The cores hint at swings the human world has never seen with its own eyes. One open question is what the sea ice actually did during those warmer past intervals. A few studies of ocean sediments suggest that summer ice in parts of the Arctic may have thinned or even broken into wide stretches of open water during certain ancient warm periods. Other studies disagree, finding signs of stubborn ice that held on through long, mild summers. The truth is hard to read because sea ice leaves only faint clues in the mud below it. Tiny shells, certain chemicals, scattered grains carried by floating ice. The picture is blurry. Researchers keep refining their tools, hoping the past will come into focus. What the cores show clearly is that the air itself is changing now in ways the record has not seen for a very long time. Carbon dioxide levels today sit higher than at any point in the ice core record stretching back hundreds of thousands of years. Methane levels are higher too. The polar regions, which respond more strongly than the rest of the planet, are warming faster than the global average. Sea ice in late summer has been thinning and shrinking across recent decades. Satellites have watched this change unfold since the late 1970s, when the first reliable measurements began. How fast the ice will continue to change and how the system will settle remains an open question. One idea is that the Arctic is moving toward a new state, with much less summer ice than the modern world has known. Another view holds that natural swings, slow cycles in winds, currents, and ocean heat, may push back against the trend in ways that are hard to predict year by year. Most researchers see both forces at work, with the long-term direction pointing toward less ice, but with details that remain unsettled. There is something humbling in the thought of those cylinders of ice resting in cold storage, each one a thin slice of deep time, a bubble of air from a forgotten winter, a speck of dust from a desert that no longer exists. Ash from a volcano that erupted before any city stood. The polar ice has been quietly writing a diary for the planet, and we are only beginning to learn how to read it. What it will say about our own century, the future will decide. The sea ice up above, drifting and grinding and reforming, is part of that ongoing entry. Its winters and its summers, its thick flows and its thin new skins, all of it is being recorded somewhere, in the mud, in the chemistry, in the slow accumulation of snow on the glaciers nearby. The story continues to be written, layer by gentle layer, while most of the world sleeps. Under the Arctic ice, the world is dim. Sunlight that strikes the frozen ceiling does not pass through easily. Most of it bounces back into the sky, scattered by snow and by the millions of tiny bubbles trapped in the ice. What does slip through is filtered, softened, turned a strange shade of blue-green. The water below glows with a faint, watery light, like a cathedral lit by stained glass that no one has cleaned in 1,000 years. In this dim cathedral, sight does not carry far. A seal looking up sees the ice as a glowing roof. A fish looking sideways sees only a few meters before the water swallows the rest. So the creatures of the under-ice world have learned to live by sound instead. Sound travels through cold seawater much faster than through air. It can race across hundreds of miles before it begins to fade. And so the Arctic, which looks so silent from above, is full of voices below. The loudest of these voices belong to whales. Bowhead whales, beluga whales, and narwhals all live beneath the ice for at least part of the year. Each species sings in its own way. The bowhead has one of the strangest songs of any animal on Earth. Its calls shift and change from year to year. A bowhead may sing one melody this winter and a completely different melody the next. Researchers who listen to them through hydrophones, small underwater microphones lowered through cracks in the ice, have counted hundreds of distinct songs in a single season. Why the bowhead changes its song is an open question. Some researchers wonder if the songs are a kind of social map, a way for scattered whales to recognize one another across long distances of dim water. Others suspect the songs are tied to mating, or to claiming a stretch of sea, or simply to the pleasure of singing. No one yet knows. The whale sings and the ice listens, and the meaning drifts somewhere between them. Belugas have a different voice. They click and whistle and chirp in such a busy chorus that old sailors called them the sea canaries. A pod of belugas under the ice sounds like a flock of small birds trapped in a glass jar. They use these sounds to find one another in the gloom, and to find the breathing holes that keep them alive. A beluga can send out a click and listen for the echo bouncing back from the underside of the floe. From that echo, it builds a picture of the ice above, where it is thick, where it is thin, where there is an opening to the air. The narwhal, with its long spiral tusk, dives deeper than almost any other whale. It plunges more than a mile down into cold black water, then returns to the surface to breathe through narrow cracks in the ice. How a narwhal navigates in such darkness, finding the one open lead among hundreds of square miles of frozen sea, is still not fully understood. One idea is that narwhals use the tusk itself as a sensor, picking up changes in salt or temperature in the water. Another idea is that they simply remember the geography of the ice from year to year, passing the knowledge from mother to calf. The truth may be a quiet mix of both. What the whales hear beyond their own songs is a world full of small sounds. The ice itself is never truly quiet. It creaks as floes grind against one another. It pops as trapped air bubbles burst under pressure. It hums with the slow scrape of pressure ridges sliding past each other in the current. To a whale, this is the background music of home, a steady, low murmur of ice talking to ice. Light shapes all of this without being seen. The thickness of the ice decides how much sun reaches the water. The amount of sun decides how much plankton can grow. The plankton feed the small fish, and the small fish feed the whales, and the whales sing into the dim, blue-green light. Every song that travels under the floes is, in some quiet way, a song made of sunlight that was bent and softened on its way down. What the whales are saying to one another remains, for now, a beautiful unknown. We can record their calls, we can sort the patterns, we can guess at meaning. But the conversation belongs to them, carried out in a half-lit room of ice and water that humans can only visit as guests. The voices go on, season after season, beneath a ceiling of white, in a language the world is still learning how to hear. The Arctic does not greet its visitors with silence. It greets them with a strange, layered music, a soundscape made by ice in motion. There is the slow groan of thick floes pressing against each other, a sound like distant doors swinging on old hinges. There is the sharp crack of new ice splitting under cold, like a rifle shot carried for miles across a frozen plain. There is the steady hiss of wind across snow, and beneath it all, a low hum from the sea itself, moving in the dark beneath the lid. The first explorers who sailed north into this world were not ready for the sound. They came from quiet harbors in Europe, expecting an empty ocean. Instead, they found a place that murmured and sighed all night. Their wooden ships creaked in answer. Sailors wrote in their journals about the strange voice of the ice, the way it seemed to speak in a language just beyond reach. Some called it singing, some called it moaning, a few called it the breath of the sea. Many of those early ships never came home. In the 16th century, an English crew under Hugh Willoughby tried to find a path across the top of the world toward the riches of Asia. Their ships were trapped by ice and cold along the Russian coast. Fishermen found them later, frozen in place, the journals still on the tables. No one knows exactly what they heard in those final weeks. We can only guess at the sounds that filled their cabins as the floes closed in. 3 centuries later, a larger expedition under John Franklin sailed into the Canadian Arctic with 2 strong ships and 129 men. They were never seen again as a full crew. Search parties found only scattered camps, a few graves on a windy island, and stories passed down by Inuit families who had watched the strangers walk south across the ice. What happened to Franklin's people is still studied today. Cold, hunger, illness, and lead from poorly sealed cans have all been suggested as factors. The full story remains stitched together from fragments, and parts of it may never be known. The sound of that vanished world is part of what makes the mystery linger. Imagine standing on the deck of one of those ships in the long polar night. The sky is black with only a smear of green aurora overhead. Around the hull, the ice presses in slow waves. It pops and pings as the temperature drops. Somewhere far away, a ridge builds itself, slab climbing onto slab with a deep grinding roar. Closer in, a seal breathes at a small hole, a soft puff in the cold. The ship's timbers answer with a long, tired creak. Modern instruments have begun to listen to the Arctic in ways those early sailors could not. Hydrophones lowered through holes in the ice pick up a whole orchestra below. The calls of bowhead whales sweep up and down in long, swooping notes. Bearded seals trill like distant flutes. Ice itself sings in low frequencies, slow vibrations that travel for hundreds of miles under the water. Some of these sounds, when sped up, sound almost like voices. Some, when slowed down, sound like the deep notes of a giant cello. Researchers are still trying to understand what the ice is telling them. One idea is that the patterns of cracking and groaning can reveal the inner structure of a flow, the hidden stress lines that show where it will break next. Another idea is that the soundscape itself is changing as the ice thins, growing more crackly and less deep, with fewer of the long, slow moans the old ships used to hear. The full meaning of these shifts is not yet clear. The acoustic record of the Arctic is young, only a few decades long, and the questions still outnumber the answers. There is something quietly moving in the thought that the lost expeditions heard a version of this music we will never hear again. Their ice was thicker, older, slower. Its voice would have been deeper, drawn out across longer winters. We can listen now to what remains and wonder how much of that ancient song has already faded. Perhaps the explorers who vanished did not vanish into silence. Perhaps they vanished into sound, into a world humming and groaning and singing all around them, a world that kept speaking long after the last journal entry was set down. The ice remembers them in its own way, in pressures and ridges and the soft echoes that travel beneath the floes. What it says exactly, we still do not know. For centuries, the people who have lived closest to the Arctic sea ice have kept a kind of mathematics in their minds. It is not written in symbols or numbers on a page. It is held in language, in memory, in the shapes of words that describe the ice. The Inuit of the North American Arctic, the Inupiat of Alaska, the Yupik of the Bering coasts, the Sami of northern Scandinavia, the Chukchi and Nenets of Siberia. Each of these peoples has spent generations learning the frozen sea by walking on it, hunting on it, and listening to it breathe. Their knowledge is precise in ways that surprise visiting scientists. Consider the simple matter of naming ice. In English, we have a handful of words: sea ice, pack ice, floe, pancake. But in the Inupiaq language of northern Alaska, researchers have recorded close to 100 distinct terms for different kinds of ice and ice conditions. There are names for ice that has just formed and is still bending under a footstep. There are names for ice attached firmly to the shore. There are names for ice that has drifted in from far away and may carry hidden weakness. There are names for thin places where seals breathe. Each word is a small equation. It tells you what the ice is doing, how old it is, what the wind has done to it, and how safe it is to cross. This naming is its own quiet form of measurement. Where a satellite might give a single number for ice thickness across many kilometers, an experienced hunter can read the same patch of ice in seconds and tell you 10 different things about it. The color of the surface, the sound it makes when struck, the way snow lies across it, the shape of the cracks, the smell of the air above it. These are signals, and the brain trained from childhood reads them as fluently as you read these words. Sami reindeer herders far to the south of the polar sea hold a similar mathematics for snow and lake ice. They keep many words for crust, for slush, for the layer that forms when rain falls on cold powder and then freezes again. Some of these terms describe conditions so specific that scientists have borrowed them when no equivalent term exists in English or Norwegian. The language itself becomes a tool of measurement. There is something elegant in this. Western science measures the Arctic with instruments. Buoys drift across the pack and send back numbers. Satellites sweep overhead and map the ice every few days. Submarines have charted the underside with sound. All of this is wonderful, and all of it is partial. The sensors see what they are built to see. They miss what they are not asked to find. Indigenous knowledge, gathered patiently across many human lifetimes, sees the ice as a living thing with moods and habits. In recent decades, scientists and Arctic communities have begun to share notes. Researchers ask elders what the ice used to do in their grandparents' time and what it does now. The answers describe changes that no single satellite record is long enough to capture. Multi-year ice that was once common near a certain village is now rare. The freeze comes later. The breakup comes sooner. Trails that families used for generations have become unsafe. The geometry of the year has shifted. Yet within these shifts, the old mathematics still applies. The names still describe what they describe. A hunter still reads the cracks. The system of knowing has not broken, even as the thing being known is changing. This raises a quiet question. What happens to a mathematics of ice when the ice itself is moving into new patterns no living elder has seen before? The vocabulary was built across centuries of relative stability. The conditions are no longer stable. Some words may need to be renewed, some may need to be invented. There is also a deeper open question. How much of what indigenous communities know about the sea ice has never been written down at all, and never been compared with the instruments of outside science? Scholars suspect a great deal. Each generation has carried small observations forward: the year a certain bay froze late, the place where a certain current rises, the sign in the sky that a storm is coming. Some of these patterns may match what physics now models. Others may describe processes science has not yet noticed. The mathematics of the frozen sea, it turns out, has always had two sets of equations. One is written in journals and on screens. The other is spoken on the ice itself, in many languages, in many quiet voices, passed from hand to hand across the long white centuries. Of all the questions surrounding the Arctic, one has grown louder in recent years, even as the place itself remains as quiet as ever. It is the question of the summer ice. Each year, the white cap at the top of the world breathes in and out. It grows in the long darkness of winter, then shrinks in the long light of summer. For thousands of years, this rhythm held a kind of balance. Enough ice melted to feed the sea. Enough ice remained to keep the pole white and cold. That balance, many researchers now believe, is shifting. The summer minimum, that smallest patch of ice left at the end of melt season, has been getting smaller. Satellites have watched it for more than 40 years, and the trend points downward. But the question that lingers in the quiet is harder than it sounds. How thin can the summer ice grow before something fundamental changes? And what exactly would change first? One theory holds that the Arctic is approaching what some scientists gently call an ice-free summer. This does not mean every floe will vanish. Some ice would still cling to the high islands and the deep north, but the Central Ocean, in late September, might one day shimmer as open water under a low gold sun. Some models suggest this could happen within decades. Others suggest the timing is much less certain, because the system pushes back in ways we do not fully understand. The honest answer is that we do not yet know which model the real Arctic will follow. What makes the question so delicate is how many tiny variables seem to matter: the brightness of the ice, the exact temperature of the air a few feet above it, the way snow lies on top or does not, the salt content of the water beneath, the strength of the winds in late August, the path of warm water flowing up from the Atlantic and the Pacific. Each of these threads pulls on the others. Tug one and the whole weaving shifts. Consider the brightness alone. Fresh white ice reflects most of the sunlight that strikes it. Dark open water absorbs most of it. So when a patch of ice melts, the water that takes its place soaks up more heat, which warms the sea, which melts more ice. This is one of the feedback loops that worries researchers most, but here is where the mystery deepens. The same loop should, in theory, also have limits. Clouds form over open water. Storms mix cold, deep water upward. Snow can fall early and brighten the surface again. The Arctic is not a simple machine. It is a slow, layered conversation between sky, sea, and ice. There is something humbling in how narrow the window seems to be. The Arctic Ocean exists at a temperature only a few degrees away from being something else entirely. A slightly warmer planet and the ice thins. A slightly cooler one and it thickens into an unbroken shield. The same is true of so many things on Earth. The air we breathe sits in a thin shell only a few miles deep. The liquid water on the surface depends on a temperature range narrower than most of us imagine. The tilt of the planet gives us seasons that the polar ice needs in order to grow and shrink in rhythm. Move any of these dials even slightly, and the world we know becomes a different world. Some researchers wonder whether the Arctic has crossed thresholds like this before. Sediment cores hint that, in deep time, the polar ocean may have been seasonally ice-free during warmer periods of Earth's past. If that is true, then an ice-free summer is not unprecedented for the planet. It would, however, be unprecedented for human history. No one alive has stood on the deck of a ship in September and seen open water all the way to the pole. Whether anyone will, in our lifetime, remains an open question. What stays unknown is how the rest of the system responds. Would weather patterns farther south shift? Would the great ocean currents slow or speed up? Would the creatures that depend on summer ice, the seals and the bears and the small lives within the ice itself, find new ways to live or fade quietly from the high latitudes? There are theories for each of these. There is consensus on very few, so we sit with the question tonight. A thin white lid, a narrow window of temperature, a balance held together by countless small things, each of them quiet, each of them ancient, each of them, perhaps, more fragile than they appear. The Arctic does not behave like a simple system. It loops back on itself in ways that scientists are still trying to map. A small change in one place can ripple outward, return, and grow. These returning ripples are called feedback loops, and the Arctic is full of them. Some are well understood, others are still mostly mystery. The most famous loop is the one between ice and light. Bright white ice reflects sunlight back into the sky. Dark open water absorbs it. When ice shrinks, more dark water shows. The dark water warms. The warmer water melts more ice. The loop turns again. Scientists call this the albedo feedback, and they understand its shape well. What they do not fully understand is its speed. How fast can this loop turn before something new takes over? No one can say for sure. There are other loops, quieter and harder to measure. Thinner ice lets more light pass through to the water below. That light feeds tiny algae living under the floes. The algae bloom earlier and in stranger places than they used to. What happens to the food web when the timing shifts is still an open question. Some creatures may find more to eat. Others may arrive too late and find the bloom already faded. The puzzle is not solved. Clouds add another layer of mystery. Over open Arctic water, more moisture rises into the air. More moisture can mean more clouds. Clouds can trap heat near the surface, or they can reflect sunlight back to space. Which effect wins depends on the season, the height of the cloud, and the kind of droplets inside it. Researchers have spent decades trying to model Arctic clouds, and the models still disagree with each other. The clouds keep their secrets. Then there is the matter of the wind. As the ice thins, it moves more easily. Storms push it around with greater force. The Beaufort Gyre spins, the transpolar drift carries ice toward the Atlantic, and the patterns are shifting in ways that are hard to predict. Some years the ice piles up in one corner of the basin. Other years it spreads thin and wide. Why the patterns shift the way they do is still being studied. The atmosphere and the ice talk to each other in a language we are only beginning to read. The ocean below adds its own voice. Warm water from the Atlantic flows north at depth, kept beneath a colder, fresher layer near the surface. That cold layer acts like a lid, protecting the ice from the heat below. Some researchers wonder whether the lid is weakening. If warm water reaches up more often, the ice would melt from beneath as well as from above. How strong the lid remains and how long it can hold is one of the deepest open questions in Arctic science. Snow plays a quieter role and a confusing one. Snow on top of ice insulates it, slowing growth in winter. Snow also reflects light, slowing melt in summer. When snow falls earlier, later, or in different amounts, the balance tips in ways that are hard to predict. A small change in snowfall can shift the whole season. The snow gauges scattered across the Arctic are few and far between. Much of what falls is never measured at all. The freshwater question is another puzzle. Melting ice and rivers pour fresh water into the Arctic basin. That fresh water sits on top of the saltier sea, changing how the layers mix. If enough of it escapes south through the straits, it could nudge the great currents of the Atlantic. How much, how fast, and with what effect remain open. The numbers are slippery. The models do not yet agree. Even the ice itself holds surprises. Old multi-year ice is more complex than new ice. It has channels, pockets of brine, layers of refrozen melt. Each of these affects how it reflects light, how it transmits heat, how it breaks under pressure. As the old ice disappears and younger ice takes its place, the physics of the cover is changing. Scientists are still learning what the new ice will do under stress, under wind, under sun. All of these loops tangle together. A change in clouds touches a change in snow, which touches a change in algae, which touches a change in the carbon balance of the surface water. No single instrument can see the whole pattern at once. The Arctic is a living puzzle with many moving pieces, and the pieces speak in different tongues. What remains unknown is not a failure of science. It is an invitation. The white lid at the top of the world still has stories it has not told us yet. Along the edges of the Arctic Ocean, where the water grows shallow and the land slides gently beneath the waves, there is a secret the seafloor has been keeping for a very long time. It is called methane. Methane is a simple gas, lighter than air, made of one carbon atom and 4 hydrogen atoms. And in the cold mud of the Arctic shelves, vast amounts of it lie locked away, frozen into strange ice-like cages called hydrates, or buried in old layers of peat that once formed dry land. Tens of thousands of years ago, much of what is now the shallow Arctic seafloor was not underwater at all. It was tundra. Mammoths walked there, grasses grew. When the great ice sheets melted at the end of the last ice age, the sea rose and covered this land. The old soil, with all its trapped carbon, sank beneath cold salt water. Some of it froze in place, sealed by permafrost, that is, ground that stays frozen year-round even under the sea, and some of the carbon turned slowly into methane. Now, as the Arctic warms, researchers wonder what will happen to this hidden carbon. Some have watched columns of bubbles rising from the seafloor off the coast of Siberia, in waters only 50 meters deep. The bubbles drift up through the cold green water and break the surface in small silvery puffs. The question is whether these methane seeps are new, or whether they have always been there, quietly venting since the seas first flooded the old plains. The evidence is incomplete. We simply have not been watching long enough to know. One theory holds that the warming sea is slowly thawing the underwater permafrost, opening cracks and channels through which methane can escape. In this view, the seeps may grow stronger over the coming centuries, releasing more and more gas into the water and, eventually, into the air. Another theory suggests that most of the methane will dissolve in the cold sea and be eaten by tiny microbes long before it reaches the surface. These microbes, invisible to the eye, feed on methane the way we feed on bread. They may be the quiet guardians of the shelf, or they may be overwhelmed. No one yet knows where the balance will fall. Try to picture 1,000,000 years from now. The shape of the Arctic itself will have shifted. The continents drift at about the speed your fingernails grow, and in 1,000,000 years they will have moved tens of kilometers. The North Pole may sit over different water. The shallow shelves may be deep basins or new land entirely. Whatever methane lingers in the mud today will, by then, have either escaped, been eaten, or been buried far deeper under new layers of sediment. The bubbles we see now will be a brief moment in a much longer story. Push the picture further. 1,000,000,000 years from now, the sun will be brighter and warmer than it is today. Long before it swells into a red giant, its slow brightening will likely have boiled away much of the ocean. The Arctic, as a place of floating ice and frozen seafloor, will simply not exist. There may be no poles cold enough to freeze water at all. The white lid at the top of the world will have lifted, not for a single warm summer, but forever. And yet new things will form. Earth has been frozen before and warm before many times. Continents have crashed together and split apart. Oceans have opened where mountains once stood. The carbon now sleeping in the Arctic mud will, on long enough timescales, find its way back into rock, into living things, into air, into the slow breath of the planet. Methane molecules that escape today may, in 100,000,000 years, be part of the limestone walls of a cave that does not exist yet, on a coastline that has not yet formed. The whispers from the shallow shelves are, in this sense, only a single line in a very long poem. We hear them now because we have only just learned to listen. Ships drift over the seeps with instruments that count each bubble. Researchers lower sensors through holes in the winter ice and wait for the soft hiss of gas. They are trying to read a story that began long before us and will continue long after. What the methane will do in the next 100 years matters very much. What it will do in the next billion is beyond our knowing. For tonight, it is enough to imagine those small silver bubbles rising slowly through dark, cold water, carrying a message we are still only beginning to understand. Step back for a moment. Step back from the ice itself, from the bears and the whales and the slow-turning gyres. Step back from the seasons. Step back from the whole white lid at the top of the world, and look at where this small frozen sea sits inside a much larger story. The Arctic Ocean is a thin film of water on the surface of a rocky planet. The ice that floats on it is thinner still. If you shrank the Earth to the size of an apple, the sea ice would be thinner than the skin of that apple by far. The whisper of frozen water, held in place by cold and salt, and the slow tilt of the planet toward and away from the sun. And yet that whisper helps shape the weather of half the world. The water in that ice is older than you can easily imagine. The hydrogen in it formed in the first minutes after the universe began, when everything was hot and bright and new. The oxygen came later, forged inside the hearts of stars that lived and died long before our sun was born. When those stars ended, they scattered their atoms into clouds of gas and dust. Some of those atoms drifted together and became our planet. Some of them became the ocean. Some of them now are locked inside a single hexagonal crystal of sea ice, drifting slowly across the pole. The same is true of you. The calcium in your bones, the iron in your blood, the carbon in every cell, all of it was made in stars. You and the ice share an origin. You are both, in the deepest sense, the cooled and gathered ash of older suns. And the question we have been sitting with all night, what will the Arctic ice look like in the years to come, is a very small question seen from far enough away, and a very large one seen from close up. Small because the Earth has been through warmer times and colder times before. There were ages when no ice formed at the poles at all, and ages when ice covered much of the northern continents. The planet has worn many faces. The ice we know is only its current expression. Large because we are alive now, in this particular moment, watching this particular face change. The mystery is not whether the Arctic will keep transforming. It will. The mystery is what shape it will settle into, and how quickly, and what the rest of the living world will do as the white lid thins. Some researchers think the summer ice may vanish within a few decades. Others think pockets will linger far longer in the coldest corners north of Greenland and the Canadian islands. The honest answer is that we are still learning to read the signs. What is certain is that the ice has always been a conversation between many things, between the tilt of the planet and the heat of the sun, between the salt of the sea and the cold of the air, between the slow currents below and the winds above, between the breath of the ocean and the breath of the sky. No single thread tells the whole story. The ice is a pattern woven from all of them at once, and it has been weaving and unweaving itself for millions of years. You are part of that pattern too, in your own way. The water in your body has been in clouds and rivers and oceans, and yes, almost certainly in polar ice at some point in its long, quiet travels. The atoms in your hand were once part of something else. They will be part of something else again. The ice teaches this lesson without speaking. Everything gathers, holds its shape for a little while, and then releases. There is something gentle about that thought as the night grows late. The frozen sea at the top of the world is not separate from you. It is made of the same ancient ingredients. It moves through its seasons. It carries its mysteries. It keeps its secrets in the dark water below and the long shadow of the polar night above. And somewhere inside that great slow breathing of a planet, a single mind drifts towards sleep, wondering about it. We may know more about the future ice in our lifetimes. We may not. The currents are slow. The cores tell their stories in tiny increments. The satellites watch year after year. The answers, when they come, will come gradually, like ice itself. For tonight, the question is enough. The wonder is enough. The quiet is enough. And so slowly we come to the end of our long walk across the ice. The wind has quieted in our story now. The pressure ridges have stopped groaning. The seals have slipped back beneath the floes, and the bears have curled into the snow with their black noses tucked beneath their paws. The frozen sea has gone still, the way a great animal goes still when it sleeps. Picture it now, that white world we have wandered through together. The ice stretches in every direction, soft under a thin layer of fresh snow. The moon hangs low, fat and yellow, painting the floes in pale gold. Long shadows stretch from each ridge, blue and patient. The air is cold and clean and utterly silent. There are no voices, there is no machinery, there is only the quiet breath of a planet at rest. Somewhere below the ice, a small fish moves through the dark. A copepod, smaller than a grain of rice, drifts past a pillar of brine. An Arctic cod hovers near the underside of a floe, where the algae grow in their slow brown gardens. None of them know we are watching. None of them need to. Above the ice, the sky has cleared. The stars come out in their old patterns, sharp and steady. The northern lights begin their slow green dance, rolling across the dome of the sky like silk being pulled through still water. They fade, they return, they fade again. The ice glows faintly beneath them, picking up that green light and holding it for a moment before letting it go. This is the planet we live on, a small, blue, half-frozen world spinning quietly in the dark. It has been doing this for a very long time. It will keep doing it for a very long time more. The ice at the top has come and gone many times across the deep history of Earth. It has been thicker, it has been thinner, it has vanished in summer and returned in winter. And through all of it, the sea has gone on breathing, in and out, the way you are breathing now. We do not know what the Arctic will look like in 50 years, or 100, or 1,000. We do not know if a child born tonight will one day sail across an open pole in summer. We do not know what the bears will do, or the seals, or the small creatures hidden in the cracks. We do not know what the deep currents will choose. There are many open questions. There are many quiet maybes. We sat with them together, and we did not need to solve them. That is the gift of a mystery. It lets you wonder without worrying. It lets you imagine without insisting. It lets the world stay larger than your own small thoughts. So let the ice drift now. Let the floes carry our questions out into the wide polar night. Let the gyre turn them slowly, year after year, the way it has always turned. Somewhere, a thin sheet of Nilas is forming on a stretch of dark water. Somewhere, a pancake of new ice is bumping gently against its neighbors. Somewhere, a beluga is singing under a roof of frozen sea, and the song is going on whether or not anyone is listening. You are warm, you are safe, the blankets are soft, the room is dim. The planet is still turning, slowly, gently, the way it has turned for 4.5 billion years. The Arctic is up there at the top of the world, doing its quiet work, and you do not have to think about any of it anymore tonight. Let your shoulders soften, let your jaw unclench, let your hands rest. Let the small worries of the day drift out onto the ice and float away with the current. They are not yours to carry into sleep. The ice has held heavier things than these, and it will hold them gently. Picture one last image if you can. A single snowflake drifting down through still air, settling onto a vast field of older snow. It makes no sound. It joins the great white quiet, and the quiet goes on and on and on over the curve of the earth, all the way to the pole and beyond. You are part of this world. The world is part of you, and tonight that is enough. Subscribe for a brand new Earth topic every night. One tap and something wonderful is waiting for you tomorrow. Sweet dreams.